I'll be explaining Bellman Ford algorithm. So this algorithm is a single source shortest path algorithm. Like there will be a source vertex, and from the source vertex we need to find the shortest path distance to all other vertices which are there in the graph. So in my previous video I have explained about Dijkstra algorithm, which was the single source shortest algorithm. The main reason to shift from Dijkstra to Bellman Ford is that if there will be a negative weights on the edge, then the Dijkstra algorithm does not perform at that time. Okay, so in order to tackle the negative weight edges, we need to use Bellman Ford algorithm. But if we compare the time complexity, we find that the Dijkstra algorithm is logarithmic time, but Bellman Ford algorithm is polynomial time. So the main thing in Bellman Ford algorithm is the programming approach. So it uses dynamic programming. Okay, it uses dynamic programming. So dynamic programming solves the problem of optimization, the problem of overlapping subproblems. Okay, so there are two types of dynamic programming approach. One is tabulation and other one is memoization. So tabulation means bottom up approach. So we are going to use bottom up approach in order to solve this problem. Okay, like we are going to start performing this Bellman Ford algorithm from the source vertex and going to initialize this source vertex as 0. So basically the distance value of vertex A to itself will be what? It will be 0. Now from source to vertex B, like for other vertices we are going to initialize it with infinity. Okay, so infinity means that suppose if there are no edges available between A to B, A to C, or like A to D, so at that time vertex B, C, D is not reachable from the source vertex. Or we can say that suppose in a graph if any vertex is not reachable from the source vertex, then that vertex must be like initialized with infinity, or at the end the distance value for that vertex from the source will be infinite. Okay, so if we see the algorithm is quite simple. I've created distance array and have initialized it with infinity. Then for source vertex I have initialized it to 0. Okay, so now we are going to perform the bottom up approach manner. Okay, like from the source vertex, first we are going to find the shortest distance path for all those vertex which are one edge length away. Okay, which are one edge length away. Then after finding the shortest distance of those vertex which are one edge length away, then we will find for the vertex which are second edge length away, and so on. So in order to find the shortest distance, we will be using relaxation. Okay, relaxation. So in Dijkstra algorithm, I have already explained what is relaxation approach, what is relaxation formula. It's nothing but suppose there is a vertex, there is an edge that is u and v. So relaxation means distance of v, if it is greater than the distance value of u. So distance value means from the source vertex to v, there will be a distance associated to it. So that is known as the distance value of v. Okay, so if distance value of v is greater than distance value of u plus weight between u comma v. So if it is following this condition, then what we can do is that we can update the weight or update the distance value, because our target is to minimize the distance value in order to get shortest path. So distance of v will be this one. Okay, it will be this one. So if we see this graph, we find that the distance of vertex A from source. So source is what? Source is vertex A itself. So distance is nothing but 0. So if we use this relaxation, what it will do is that it will change or minimize the distance value of the vertex which are reachable at one unit edge. So if we see this A to B, so the distance value of B is what? Infinite initially. So it will be changed to 1 because 0 plus 1. 1 is nothing but the weight between U and V. So it will be 1. And if we see the adjacent vertex C, we find that the initial value is infinity. So 0 plus 4, 4 is less than infinity. So we'll update the distance value of vertex C to 4. So it will be updated to 4. So this is nothing but relaxation. Okay. So this relaxation of edges ensures that there will be a minimum weight between U comma V. Okay. Minimum weight for the edge connecting U and V vertex. So we are going to perform this relaxation operation till V minus 1 iterations. So there are suppose 4 vertices. So we are going to perform relaxation of all the edges till n minus 1, that is 3 times. Okay. So we are relaxing all the edges 3 times. And why we are relaxing all the edges 3 times? Like why we are performing V minus 1 iterations? Because shortest path is nothing but a simple path. So what is simple path? A simple path is the sequence of vertex and edge in which there will be no repetition of vertex as well as no repetition of edge. So vertex and edge will not be repeated. So this is known as a simple path. So if we draw a graph and find the simple path, suppose this is a graph. This is U, the source vertex. We move to this vertex, then we move to this vertex, suppose. Okay. And this is some final vertex. Okay. From U to V, I need to find the shortest path. So what will be the shortest path? The shortest path will be nothing but the shortest path of U and U dash, U dash to U double dash, and U double dash to V. So shortest path is a set, or it's a combination of smaller shortest path between the vertex. So if we need to find the shortest path between U and V, we need to find the shortest path from U to U dash to U double dash, and then U double dash to V. By this way we can find the shortest path between U and V. So shortest path is a simple path. So if we see this, we find that there are 4 vertices in this simple graph. So if there are 4 vertices, there are 1, 2, 3 edges. It means that we need to perform relaxation operation for edges 3 times. Okay. Because in simple path vertex is not repeated. So if vertex is not repeated, in order to have n vertex which are not repeated, will have n minus 1 edges connecting that vertex. So we need to perform relaxation operation for n minus 1 times, and relaxation operation ensures that edge connecting the vertex will get minimum value. Okay, it will get minimum value. So this is the reason we are having V minus 1 iterations. Okay. And after that, what we have to do is that, suppose like we need to find the edges. So if we see in the graph, the edges are AB, BC, CD, BD, okay, and AC. So these are the edges. Order of edges can be in random order. So order can be in any random order. Okay. So how we can solve this problem? How we can find the shortest path from vertex A to all other vertices? So first of all, I'll write all the vertex A, B, C and D. Okay, so this is the vertex and I'll write the distance. So distance of vertex A from source vertex is what? It's 0. And all other vertex, I've already initialized it with infinity, because we are considering that right now no edges are connecting B, C and D with the source vertex. Okay. Now after that, what we have to do is that we need to perform relaxation operation, and relaxation is nothing but d of v if it is greater than d of u, where d of v is the distance value of vertex v from the source, d of u is the distance value of vertex u from the source, plus weight associated between u and v edges. Okay, weight associated to the edges connecting u and v. So if it is true, then we need to change the value, because each relaxation ensures the shortest weight connecting the vertex. Okay, after that we need to have a for loop performing v minus 1 iterations. So if there are 4 vertices, we need to perform 3 iterations. Okay, for every edge u comma v, suppose like b and c. So if we see in this table, we find that the value of b is what? Infinity. And the value of c is what? Infinity. So suppose b is u and c is v. So distance of b is what? Distance of b is infinity. Okay, infinity is greater than distance of u is what? Distance of u is also infinity, and weight associated between vertex b and c is what? It's minus 3. So it is nothing but infinity. So this condition is false. Relaxation condition is false. Okay, it means that b and c will remain infinity. Now next edge is b and d. So b is what? B is infinity. Okay, d is also infinity. So if both are infinity, no relaxation will perform. Next edge is c and d. So distance value of c is infinity, distance value of d is infinity, no relaxation will perform. Next is a and b. So distance value of a is 0 and b is what? B is infinity. So if we see in the graph, we find that 0 plus 1. 1 is the weight and 0 means distance of u. So 0 plus 1, 1. 1 is less than infinity. 1 is less than infinity. So what I will do is that I'll cut infinity and I'll change it to 1. Okay, so it will be 1. Distance of b will be 1. Now a to c. C is infinity but a is 0. So if we use relaxation of edge connecting a and c, what it will do, it will change the value from infinity to 4. So in first iteration, all the vertex which are one edge away, we got the shortest distance connecting to that vertex. Okay, so if we see in the graph, we find that a to c and a to b, they are vertex b and c are one edge away, and we have got the shortest distance connecting from source to that vertex. Now next, this is the first iteration. So what will be the second iteration? Again we need to relax all the edges. So if we see b and c, so b is 1 and c is 4. Okay, so 1 minus 3. 1 minus 3 is minus 2. So we can reduce the distance value of C to minus 2. Okay, next is B and D. 1 plus 2, 3. Okay, so we can change it from infinity to 3. Next is C and D. C and D. So the distance value of D is what? It's 3. But if we perform relaxation of edges connecting C and D, we find that it's 4 plus 3, 7. So we'll not change the value. Next is A and B. So A and B, if we see, it's same, it's 1 only, will not change the value. Next is A and C. So A and C is 0 plus 4, 4, but the current distance value is minus 2, which is minimum. So we need minimum value. So we'll not perform relaxation. So we got this in second iteration. Okay, now we'll perform the last iteration. So again we need to perform relaxation of all the edges. So if we see B and C, if we see in the graph, we find that C is minus 2 only. 1 minus 3 minus 2. The distance value of C is minus 2. Will not change. B and D. B and D, if we see, we find that 1 plus 2, 3. Okay, it's same. Next is C and D. So the distance value of C is minus 2 and D is 3. It means that if we perform relaxation, we find that it's reducing distance value of D. So it will be 1. Okay. Next is A and B. A and B will remain same. 0 plus 1 is 1. Okay. Next is A and C. So A and C, the distance value of C is minus 2. If we perform relaxation operation between A and C, it will be 0 plus 4, 4, which is maximum. So we need not to change the value of this. So after third iteration, we got this value. So third iteration, we got this value. So this will be the shortest distance path from the source vertex to these vertex, to these vertices. So our source vertex is A. So A to A, the shortest distance path will be 0. A to B, the shortest distance is 1. A to C, it's minus 2, and A to D, 1. So if we see in the graph, like we need to move from A to D using shortest distance path. So we'll see it's 1. So we can have this 1 minus 3 and 3. Using this path, we can reach from vertex A to vertex D, which is the shortest distance path. So by this way, we can solve Bellman Ford algorithm. So this is the simple algorithm. If we see, we find that we are having this for loop for v minus 1 iterations and for every edge. So for every edge, there are total edges, suppose e edges, and v minus 1 iterations is nothing but approximately v. So it's nothing but we go of VE, which is polynomial time complexity. So the time complexity of Bellman Ford algorithm is VE. Bellman Ford algorithm, the time complexity is big O of VE, which is a polynomial time. It is used to find the shortest distance path from single source to all other vertices. So it's known as a single source shortest path algorithm. And next application is that it is used to detect negative weight cycle. So Bellman Ford algorithm does not give correct answer if there is a negative weight cycle. So if there are negative weight cycle, this Bellman Ford algorithm, what it will do, it will report to the main system that there is a negative weight cycle, so that main system can remove that network which are making negative weight cycles. Okay, so we need to perform v minus 1 iterations, because in a simple path, which is nothing but in a shortest distance path, there will be v vertex which is not repeated. So there will be v minus 1 edges connecting to that v vertices. Okay. But if we perform the next iteration, for example, if there are total four vertices are there, so we need to perform third iteration. On performing third iteration, we'll get the values corresponding to each vertex, which will indicate the shortest distance value from the source vertex. On performing the next iteration, if the value gets changed or gets reduced, if the value remains constant, performing fourth, fifth, sixth iteration or more, like max is number of edges up to number of edges iterations. If the value remain constant, it means that the value you have achieved in n minus 1 iterations is the shortest distance value. Okay, but if the value gets reduced, if any one value gets reduced, it means that there is a cycle in that graph. Okay, there's a cycle in that graph. And why? Because if the value is reducing, it means that the vertex is repeated. Okay, if the value is reducing, if the on performing one extra iteration or more extra iterations, after completion of v minus 1 iterations, if any one value gets reduced, it means that there is a vertex which is repeated. It means the path is not simple. So if the path is not simple, it means vertex is repeated, and if the vertex is repeated, it means there is a cycle in a graph. Okay, there's a cycle in a graph, and that cycle is reducing the shortest distance value. If it is reducing the shortest distance value, then it means that some negative weights are associated to that cycle. Okay, so by this way, Bellman Ford algorithm detects negative weight